Hello everyone, my name is Adriano Camps and I'm going to present these recent results on GNSS reflectometry at UPC on behalf of the team formed by myself, Joan Francesc Muñoz Martín, Gil Park and Adrián Pérez, belonging to the Unitat Maria de Maez II Comsens Lab at the Universitat Politécnica de Catalunya. The outline of this presentation is the following. First, we will revise the past activities in GNSSR. Then we will revise the microwave interferometric reflectometer and will present some experimental results over the ocean and over land. We will also present a test bench that we have developed to test spaceborne GNSSR instruments, and then two simulation activities, one developed to the simulation of GNSSR observables over land and over the ocean, and a simulation experiment about embarking GNSSR instruments in commercial aircrafts. We will finalize this presentation introducing the FSSCAT mission, our participation in the Mosaic expedition for the calibration, validation, and model development for FSSCAT, and some first results. Our activities in GNSSR date back to the year 2000. In 2001, we had already developed our first instrument, Derek, that included 3 channels, 2 looking down and 1 looking up, recording raw signals at 20 megasamples per second. Then, and thanks to an ERC URI award, in 2004, we developed GRIPAU and PAU, which was the first instrument computing DVMs in real time. We also developed a spaceborne instrument, PAU, for the INTA microsat mission, but unfortunately the mission was cancelled. We developed the Picaro instrument for the CubeSat-2 satellite. And then these are our 2 current missions, CubeSat-4 that we are developing now, and FSSCAT that is flying at present. We have developed other instruments like the SMIGOL implementing the interference pattern technique, and for smaller instruments like Largo and Corto that implement GPS reflectometry L1 for the CE code only in real time for ground-based applications, for airborne applications, even from a parapent. And then our jewel of the crown, which is the MIR instrument that will be presented in the next slides.
MIR is a GPS and Galileo L1, L5, E1 and E5A GNSSR instrument conceived to perform conventional and interferometric GNSSR, storing the raw data at 1 bit precision. The instrument is composed by 2 very high directive antennas with several beams that are able to automatically track the transmitting satellite and the specular reflection point. The instrument flew on an airplane, as you can see in the image, over Bass Strait, it's over the ocean in Australia, on June 2018, and also over Yanko, a radiometric calibration area over Australia, in 2 flights, April and June 2018. And thanks to these high directive antennas and the raw data that we have available, several novel techniques and analyses have been possible. The first analysis was conducted over the ocean of this Bass Strait flight. Basically, thanks to these formulas we can see here, we are able to untangle, thanks to the variance property of the signal, the coherent and incoherent component of the GPS L1CA signal. As you can see in the image, the direct signal, even with 40 millisecond sampling, has the same coherency as the total power waveform, which means that the coherence is not being lost. However, for the reflected waveform, as you increase the integration time, the coherent component decreases, as you can see in this first example, as 1/3 of the total power waveform. This is basically due to the loss of coherency on the phase evolution of the signal. As you can see, after more or less 20 milliseconds of integration, the phase of the reflected peak is lost. Furthermore, in L5, during the processing of this raw data, we found several peaks, so multiple peaks in the L5 waveform at the Doppler cut. As you can see in some of the examples, we can relate the distance between 2 consecutive peaks with multiple specular reflections over different wave crests. Thanks to that, and doing a Fourier analysis on the time series of this distance, so the distance between this first peak, so the specular reflection point, and this second peak, and taking a look to the Fourier transform, we are able to see in the periodicity of this magnitude the swell period around 0.1 Hz, and also the wind-driven period 0.2 Hz, which is basically 5 seconds for the wind-driven period, which was actually the data from the icon model, and also the swell period around 9 and 20 seconds, also consistent with the icon model. Finally, Mir flew over land in two different scenarios. One, after more than 1 month without any rain at all over the area, and then the second flight after a very rainy journey. Was raining for a couple of days continuously, and we flew just the day after. We cross-calibrated the L1 and L5 beams using water bodies, as you can see in the image, some rivers and lakes, and then we computed, in this case, the histogram of these reflectivities for different beams and the different flights, and as we can see, even the mean value has 4-5 dB of this difference, which is the expected value out of the soil moisture difference between the two flights. We have a large dispersion on the histogram, standard deviation around 5 dBs, which means that the surface roughness plays a very important role attenuating and making a variation of this signal. Also, to remark that the mean reflectivity drops on those areas that are highly vegetated or they are rougher, as we can see in the image with these red circles. Areas with some changes on the terrain correspond to a change of the mean reflectivity value.
Techniques such as GNSS are difficult to test due to the high cost of GNSS simulators. For this reason, we created a plug-and-play software-based GNSS simulator for GNSS and GNSSR instruments. The simulation obtained GNSS satellites' positions at a specified time and modified their transmitted signal and message to account for the transmission path, be it directly from GNSS satellite to receiver or through the reflection on a rough or still surface. The output could be injected directly to software receivers, such as the one used in the FSS-CAD mission for testing purposes, or transmitted through a software-defined radio to test hardware receivers. With this, we could assess the performance of spaceborne GNSSR instruments with reflected signals, the performance of GNSS receivers in high dynamics, and the effects of RFI on both GNSS and GNSSR instruments. As an example, in the pictures below, the generated reflected signal can be seen before and after the introduction of RFI, and afterwards the recovered signal after RFI mitigation with the Phoenix hardware.
Now I'm introducing the end-to-end simulator. We have developed the web-based simulator in order to study the relationships between the GNSS measurements and many parameters. For example, observation geometry and like elevation angle and geophysical parameters. For the land case, they are topography or soil moisture and so on. And the ocean case, they are sea surface wind speed and directions. We have developed two versions of simulator, one for land and the other for the sea. So you can run simulation on the web by accessing these web addresses. The simulator has two simulation modes. One is parameter sweep mode, which helps efficient study on the impact of each geoparameter on the DDM. And the other mode is called orbit propagation mode, which can reproduce or pre-simulate the spaceborne mission. What kind of studies could we utilize the simulator? From the parameter sweep simulation, we can efficiently simulate the dependence of DDM on the geoparameter. In other words, we can do sensitivity study like soil moisture and vegetation and see surface wind speed. The simulation also can simulate the actual spacebound measurements as orbit propagating. This is an example of the TDS-1 simulation when ground track crossing the Amazon River. Various geoparameters are read from the database, for example, soil moisture, inland water fraction, and forest fractions. The scattering map or scattering image over the glistening zones are consecutively constructed according to the orbit propagating. And finally, by using this scattering image, we can get the DDMs generated from the simulator. Using these simulations, you can analyze the DDM corresponding to the reflect Earth surface condition, and also we can compare them to the actual measurements of the TDS-1. So we can apply this web-based simulator for the efficient study of GNSS spacebound study.
The main idea behind this work is the sheer amount of planes that are on flight at any given moment. Instruments that have been mounted on airplanes have improved spatial resolution and revisit time over the flight routes than spaceborne ones, mainly due to the smaller Fresnel zones as a byproduct of the reduced height. For this study, real plane positions were stored starting in July 2019 every 10 seconds, with the objective to simulate the specular points that each plane would be able to capture. For each plane in the world and for each 10-second window, 5 to 12 specular points corresponding to a different GPS satellites in view were calculated, with a precision greater than 10 meters. This resulted in a very big amount of data during the whole year, but just after one day, the specular points would cover large amounts of land and sea, as you can see in these videos. The top one is focused on Florida, which at the time was 6 p.m., and the bottom one in mainland Spain at around 3 a.m. local time. This huge amount of data prompted for smaller case studies and aggregation in 1 kilometer hexagonal grids every 3 hours for ease of processing. Mainland Spain was focused to calculate some representative statistics. What we obtained was that up to 90% of all mainland Spain, including the Balearic Islands, was covered by airborne GNSS in a single day. Averaging the revisit times per hexagon yielded around 1.2 reflections per 3-hour slot, with a standard deviation of 1.8. By using this technique, it would be possible to obtain weather nowcasting measurements by downloading them using low Earth orbit satellite internet services.
And now we are going to present the FSSCAT mission. FSSCAT is an innovative mission consisting of two federated 6-unit CubeSats, CubeCat-5A and CubeCat-5B. It was the winner of the 2017 ESA Sentinel Small Satellite Challenge and 2017 overall Copernicus Masters competition winner. The payloads of CubeCat-5A are the Flexible Microwave Payload 2, a dual microwave payload, a microwave radiometer, and a GNSS instrument combined in a single instrument using a software-defined radio. It also includes the Federated Satellite System experiment and an optical intersatellite link to communicate both spacecrafts. Among the science objectives, we have the measurement of soil moisture, ice thickness and extent, and the detection of water ponds over the ice. CubeCat-5B includes HyperScout 2, which is an hyperspectral imager combining linear and thermal infrared channels. It also includes the Federated Satellite System experiment and an optical intersatellite link. And among the science objectives are the terrain classification and pixel downscaling to enhance the soil moisture, the spatial resolution of the soil moisture products, the cross-calibration with Sentinel-2, and it is enhanced with FISAT-1 experiment, which is an onboard processor for cloud detection using artificial intelligence.
Aside from FSSCAT, we also developed a calibration and model validation activities on top of the sea ice. We developed a circular polarization GNSS instrument, which is the one at the very first figure at the left, that is part of the Mosaic campaign over the Arctic Sea. The campaign basically locates some remote sensing instrument on top of a floe, and they are activated for the whole year just to measure. In our case, we found that a very interesting interference pattern was produced by the interference of the direct and reflected GNSS signals. In this case, showing that we were able to infer snow thickness and ice thickness. And one very important result is that the snow thickness is more sensitive rather than the ice thickness for the GNSS. But let's move to the results from FSSCAT from FMPL2, the L-band and GNSS instrument on board CubeCat 5A. The very first result presented here is out of the radiometer, which is composed by a very large footprint antenna following a total power radiometer technique. In this case, measurements are taken with a 2 Hz frequency, and as we can see in all the three images, we are now measuring the North Pole and also the South Pole. And as we can see, we can identify where the sea ice starts to come thanks to the gradient of the brightness temperature evolution also in the North Pole. Thanks to that, we can provide low resolution sea ice extension maps. But what if we combine this data with GNSS? We also identified a change on the reflected power. And here we can see as we get into the ice, the reflected power gets slightly attenuated as compared to the ocean. And in this case, using a combined algorithm, we could have a greater resolution sea ice extension map. In this case, a sea ice classification algorithm based on a 4-level decision tree shows a significant correlation between this combined GNSS and L-band radiometer combined product to the sea ice extension product from OSISAF. Just some examples. As you can see here, we are able to see, in this case, in green is identified as very thin ice or new ice, and in light blue we can, and also in red in our track, is a multi-year or thicker ice in this case. Thank you for your attention.